This is problem set number 5, problem 5. Positive charge Q is distributed uniformly along the positive y-axis between y equals 0 and y equals a. A negative point charge, negative Q, lies on the positive x-axis, a distance x from the origin. Calculate the x and y components of the electric field produced by the charge distribution Q at points on the positive x-axis. And part B, calculate the x and y components of the force that the charge distribution Q exerts on Q. I know the problem set has a part C, but frankly, I have not been exposed to Taylor expansion and need to review that. Haven't been exposed to it in a few years, so I'll have to review that. So for that reason, I'm just going to cover part A and part B. Okay. So the problem states that negative point charge Q, or negative Q, which is this guy right here, is a distance of x from the origin. So we're going to call this, we're going to call this distance x, okay? So for part A, calculate the x and y components of the electric field produced by charge distribution Q at points on the positive x-axis. So this rod is going to have infinitesimally small charges, right? Or it's going to have a charge. I'll use a different color, maybe blue. It's going to have a charge here, a little tiny charge there, a little tiny charge here, a little tiny charge there, a little tiny charge there, and so on and so forth. That will run all the way along this positively charged line, this line charge, right? From 0 all the way until it reaches A, right? So let's say one of those infinitesimally small charges is located right here, okay? And it has a tiny charge dq, and it has some little y or some little length dy, okay? And that distance from the origin, we're going to call, if this one we called x, let's say that each little dy right here, so this is also dy, right? Every time we switch, x is constant, however, y is not. So for each little dy, this we're going to call y, right? And this we are also going to call y right here. So just wherever our dy is, we're going to call that y. All right? Okay. So this will be, this will be distance y from origin. All right, and this is a 90-degree angle, right? So it's going to have, this will hit our point right here, negative point charge Q, but just that location for negative point charge Q at an angle of theta, right? Because this little dy or this little dq charge emits an electric field on this guy, right? On that location. And because dq is positively charged and our electric field is experienced by something with a positive charge, right? Because electric field always points to where a positive charge would point. Then we know that the dE that the electric field that this location would experience because of this specific dq right there would point towards this direction, right? So that would be our dE that we experience, right? And again, this is theta. Okay. What else can we say about this? If we've got this triangle right here, and I know that this side is x and this side is y, what would be my hypotenuse? Then this would be this distance r. All right, that's r is the distance between the center of charges, and the two charges are this this charge right here, this our location here, and the dq right here. That would be r equals square root of x squared plus y squared, right? That's just Pythagorean's theorem. Okay. So for part A, let's calculate the x and y components of the electric field. So Ex and Ey. All right. I'm going to draw my dE out so that I could have a better visual of it. So if I have this x, y axis right there, that's my coordinate system. And okay, I've got that. This is y, this is x, okay? And I have some dE going this way. This is dE from this point. And as we said, this angle is theta, right? So this is just this guy. Okay. So obviously, that's going to have an x and y component, right, associated with it, and so that would be this guy right here. This would be our dx. So dEx, the x component of the electric field, and then this would be the y component of the electric field, or dEy. This is 90 degrees, right? 1 second. Just had to turn on the lights. Okay, so now I'm going to use Coulomb's law for a line charge, that formula, to find my dE. So Coulomb's law for a line charge is dE is equal to k dq over r squared. Okay. And I just want to clarify that this dq that you see here, this is the dq of the source charge. That's that infinitesimally small portion of the source charge. Okay. So in our case, right, looking at the at this picture provided in the problem, that would be this dq right here, because that's that infinitesimally small source charge. So d capital Q, right? And this r right here in the denominator, or the r squared, but you just want to focus on the r right now. That is the distance between center of charges. So in our case, again, looking at the picture provided in the problem, this is the distance between the two charges. So that would be x squared plus y squared, the square root of that. Okay. So I guess I'll write this down. This r is distance between two charges. Or for the case of an electric field, I guess it's the distance between the point of where we want to find out the electric field of and the source charge. Okay, so plugging in this formula, but in terms of our problem, you would get K, which is the electrostatic constant, times what is our infinitesimally small source charge? Again, it's D capital Q for this case, right? Divided by our distance between the source charge and the point where we want to find out the electric field of is square root of x squared plus y squared. And then we square that because of this square right here. Okay. And now let's break that down even further. Okay, so if our so we'll call this side quest 1. If the linear charge density gamma is equal to Q over L, with this being the total charge and this being the total length. In the case of our problem, the total charge is indeed capital Q, so we'll leave it as that. But this time the total length that we're dealing with is from 0 to A, right? So I'm going to call this, instead of total length L, I'm going to call it total length A. I'm just plugging in the variables that I was given. Okay. And so if we look at our infinitesimally small source charge, dq, it would be, again, even though this is a small piece of the total linear charge, right? This uniformly charged rod, even though this is just a small piece of it, the density doesn't change. It's the same as saying, is a glass of water or is 12 feet of steel, does it have the same density as 2 feet of steel? Yeah, because the material is the same, so it has the same density. Density doesn't change, right? So then we'll still keep this as gamma, or linear charge density. And then we'll just multiply that by this little dy that we have here. The size does change. So now we won't go the full y or the full a. We're just going to call it dy, right, for a little dq. Okay, so now let's plug in gamma as q over a, which is what we've got up here, right? That's gamma, q over a. So dq is equal to q over a times dy. All right, and we're going to use this. Also, we're going to substitute r, which we already did, as x squared plus y squared, right? Square root of x squared plus y squared. So that, we already explained why that was, so that's fine. So now let's go ahead and do that. Oh, another thing, if you guys don't have this in your cheat sheet, it's probably going to be helpful to have it, but the value for k is equal to 1 over 4 pi epsilon naught, right? That's the value for the electrostatic constant. And epsilon naught is the permittivity of free space. And it's a value or a measure of how well the electric field works in a vacuum. That's this guy, the permittivity of free space. Okay, so let's substitute those in, and we would get 1 over 4 pi epsilon naught times, instead of dq, we're going to say q over a times dy, and then 1 over square root of x squared plus y squared, right? And so if I kind of bring all that together, I would get q divided by 4 pi epsilon naught times a times x squared plus y squared. Yeah, that would be it, because the square root cancels out with a square. Okay, so this would be my value for my dE. Okay. Oh, don't forget the dy. So we get a dy there too. All right, but that's not what the question was asking for, right? Question A, or part A, is asking for the x and y components of electric field. So looking at this graph that I've drawn, we were able to find the dE right here. Now let's break it into x and y components and get the dEx and dEy, right? Okay, so based on this triangle that we've drawn with angle theta, we can say that dEx is equal to dE times cosine of theta. All right. And we could also say that dEy is equal to, I'll put this in a little, I'll give it a little barrier. So dEy is equal to, by the way, the sign for dEx obviously is positive because it's pointing towards positive x direction, right? What about the dEy, the y component of dE? It's pointing down towards negative y direction, right? So we know that that will be minus dE sine of theta, right? Sine because it's the opposite of the angle theta. It's the opposite side of the angle theta. And for the x component, cosine because it's adjacent to the angle theta. All right. Again, let's look at our, let's do another side quest here to plug in what would be the value for the cosine and sine of theta, these guys. Okay. Looking at this picture given in the problem, right? If this is theta, what is the cosine of theta? Again, let's use that SOHCAHTOA that we learned. SOHCAHTOA. Okay. So the sine of theta would be opposite, which is y, over the hypotenuse, which is square root of x squared plus y squared. Okay. And the cosine of theta would be, if this is theta, the cosine of theta would be x right here over the hypotenuse, which is, again, square root of x squared plus y squared. All right, so let's just make sure we write that down, that for side mission number 3, cosine of theta is equal to x over square root x squared plus y squared, and sine theta is equal to y over x squared, or square root of x squared plus y squared. Okay? So now let's plug those values in, all right? We already know that our dE, that's equal to q over 4 pi epsilon naught a times x squared plus y squared dy, but I'll leave that till the end. And the cosine value, cosine of theta is, so we multiply that by x times x over square root of x squared plus y squared dy, right? And I could bring those together, the x squared plus y squared. So I would get qx divided by 4 pi epsilon naught times a, and then x squared plus y squared to the 3/2, right? 3 over 2. Because x times square root of x, or x to the 1/2, that's the same as saying x to the power of 2 over 2 times x to the power of 1/2. That would just be 2 over 2 plus 1/2. So then that would be x to the 3/2, right? Okay. So that is our answer for, oh, don't forget dy. That's our answer for the x component of the electric field. Or no, the dex, not the x component, but the dex. And then for dey, we would get, and let's put a barrier over here so we know to find it later on. For dey, that would be negative q divided by 4 pi epsilon naught times a times the square root of x, or times x squared plus y squared. Okay, and then sine theta, that would be times y over square root of x squared plus y squared dy, right? And then again, I'll bring those together. So that would be negative q divided by 4 pi epsilon naught times a times y, and then in the denominator, I would have, bringing these two x squared plus y squared terms together, x squared plus y squared to the 3/2, right? dy. That would be my dey. Okay. So that's the dex and dey that I get for each of these little dq's, right? But what the problem is asking me for is the total electric field, or the electric field produced, the x and y component. So I'm going to need to add up all these little dy's, or the electric field from these little dq's, right? Until we go from 0 all the way to a. Okay? All right, so in order to do that, I'll start with Ex, my x component of electric field. In order to do that, I would need to take the integral of dex, right? The integral of dex will give me Ex. So I'm going to use this value, which we calculated for dex, and integrate it from 0 to a, which is the total length of our uniformly charged rod. Like, we go from 0 all the way to a. And I'm going to take out the constants as well while I'm at it. So that take out x, or q and x, since x is constant throughout the problem, over 4 pi epsilon naught and a. These are all constants, right? And I'm just going to leave the rest inside the integral because I need to integrate them. And that would be x squared plus y squared to the negative 3/2 because it's in the denominator. So negative 3/2 dy. Okay, I'll make this a little smaller. Okay. So I'm gonna go on a little side mission again to get the integral of this guy, okay? Then I would put that on the bottom. So here I'll have qx over 4 pi epsilon naught times a, and then let's do side mission to get the value for this guy. All right. So I'll use brown for side missions. So side quest, I think this is number 4. Yeah, because this one was 3. Okay, this is side quest number 4. Okay, so we want to find the integral of x squared plus y squared to the negative 3/2 dy, right? I'm going to rewrite that as the integral of 1 over x squared plus y squared to the 3/2 dy. Okay. And then I'm going to say I'll use green. I'm going to say let y equal x tangent. Let me move a little bit. Let y equal x tangent of u. Okay? X tangent of u. So if I let y equal x tangent of u, my dy is going to be equal to, x is just a constant, so that's x. The derivative of tangent of u would be secant squared of u, right? Or 1 over cosine squared of u. So therefore, my derivative dy would be x, because that's a constant, over cosine squared of u, du. All right? And now I'm going to plug these in back to our side quest number 4. So that would be the integral of 1 over x squared plus, instead of y squared, I'm going to say x squared tangent squared of u. Yeah, because we let y equal x tangent of u, so y squared is x squared tangent squared of u. And that was to the 3/2, right? I'm going to multiply that by, what is dy? dy is now x over cosine squared of u, du. Okay? Obviously I can see that I have an x squared here and an x squared here in this other term, so I could factor the x squared out. And that would be 1 over x squared times 1 plus tangent squared of u, again, to the power of 3/2. That'd be multiplied by x over cosine squared of u, du, right? So I'm gonna distribute this power to this term and this term, okay? So then I would get 1 over x squared to the power of 3/2 would just be x cubed, right? Because the 2's would cancel out. And then times 1 plus tangent squared of u to the 3/2, right? Because in this case, this squared and this 3 over 2, the 2 part in the denominator would cancel out, right? Okay. And then I would still multiply that by x over cosine squared of u du. All right, now I could cancel out these x's, and this becomes to the power of 2, right? And then I would be left with integral of 1 over x squared times 1 plus tangent squared of u to the 3/2 times 1 over cosine squared of u du, right? And I could actually take this 1 over x squared out because that is a constant. X is a constant, right? So I'll go ahead and do that. So then I'm left with 1 over x squared times the integral of, what is 1 plus tangent squared of u? So 1 plus tangent squared of u is equal to the secant squared of u, okay? That's just a trig identity, right? Or a trig substitution that we could do. So that's something you should either know or might be helpful to have it in your cheat sheet. So using that substitution, I'm going to go ahead and end up with 1 over secant squared of u to the 3/2. Oh, sorry, I wrote in black. One over secant squared of u to the 3/2, okay, times 1 over cosine squared of u du. And again, if I distribute this power there, my 2 secant squared would cancel out with the 2 in the denominator. So I would be left with, 1 over x squared, integral of 1 over secant cube of u times 1 over cosine squared of u du, right? And remember that cosine of x is equal to 1 over secant of x, right? So using that knowledge, I could change this. Actually, I'll write this in blue here. So cosine of x, or let's call it u. Cosine of u is equal to 1 over secant of u, right? And using that knowledge, I can then change this into cosine cube of u. I'm basically just inverting this guy, right? So that becomes cosine cubed instead of 1 over secant cube of u. And then in the denominator, I have divided by cosine squared of u du. And this guy, I just moved. So I just put them together, okay? Again, I'll clarify. This term became this numerator, right? 1 over secant cube of u is just cosine cubed of u. And this term, I just left in the denominator, all right? Okay, so that simplifies to 1 over x times the integral of cosine of u du, right? So that becomes 1 over x, and the integral of cosine is just sine, so that becomes sine of u, okay? And, oh, this is x squared. All right, and what is the sine of u? What is the sine of u? That is the same as saying, what was u? U was equal to remember, y was equal to tangent x, or y equals x tangent u. So then u, I'll write that down. So since y was equal to x tangent of u, then u would be equal to y over x, the inverse tangent of y over x, right? So now I'm going to substitute that here. That would be inverse tangent of y over x. Okay. And if this idea of seeing sine and then a tangent, inverse tangent inside the sine scares you because it looks confusing, but actually let's look at it through visually. We'll see that it's actually not that bad. Let's look at it. So first let's look at the inverse tangent of y of x, right? If we go back up to this picture right here, the inverse tangent, so tangent is opposite over adjacent, right? So the tangent of theta is opposite y over x. So if the tangent of theta is y over x, then the inverse tangent of y over x is just theta, right? So I'm going to plug theta in here. So that becomes 1 over x squared sine of theta, right? Because that's what the value is for the inverse tangent of y over x. Okay, so now that we got that, let's plug in the value for sine of theta. Again, sine is opposite over the hypotenuse, right? So if this is our theta, sine of theta would be opposite, or y, divided by the hypotenuse square root of x squared plus y squared, okay? So let's do that. So this becomes 1 over x squared times, instead of sine theta, like we said, we'll opposite, which is y, divided by the hypotenuse, which is square root of x squared plus y squared. Okay, not too bad. Now that's the final answer for this guy. The integral of x squared plus y squared minus to the power of minus 3/2 dy. All right. So that was, again, that's just this guy, right? So let's write that back down because that's the answer. So that. I'm going to move this a little bit. That was equal to the integral of x squared plus y squared to the negative 3/2 dy, right? And that's what we wanted to find. Okay. So I'll plug that in. That was a long side quest, number 4, but no worries, we got it. So here I'll plug in 1 over x squared times y divided by the square root of x squared plus y squared. Okay? And that goes from 0 to a, right? So obviously we plug in a for any y terms, and then minus, we plug in 0 for all the y terms, right? So then that becomes equal to qx divided by 4 pi epsilon naught times a. And then we could remember this is a constant, x is a constant, so we can pull that out too. So divided by x squared in the denominator. And then we would get times a divided by x squared plus a squared minus 0. Because when you plug in 0 for y, you would get, that would be 0, right? Okay, so since that's 0, then we would get equals qx a, or actually these a's would cancel out. This a will cancel out with this a, right? And this x will cancel out with the x squared on the bottom. So we will be left with qx divided by 4 pi epsilon naught x. Oh wait, there's no x in the numerator, sorry. Square root of x squared plus a squared. Okay, that is our x component of electric field produced by charge distribution Q. So that's 1/2 of our answers for part A. All right. I know that was kind of a long one, but we're getting there. Now let's look for the y component of electric field. So for the y component of electric field, that is going to be equal to the integral of dEy, the y component of dE, right, which we solved for earlier right here. So I'll just plug that in and take the integral of that. So that is equal to, I'm going to take out the constants, and the constants here are minus q, 4 pi epsilon naught, and a, right? These are constants. So I'm going to bring that out of the integral. So minus q divided by 4 pi epsilon naught times a times the integral from 0 to a of y divided by x squared plus y squared to the power of 3/2 dy. Okay? Now I'm going to let u be equal to x squared plus y squared, right? And so if I take the derivative of that, du would be equal to, this is just a constant, so that's 0, and then the derivative of y squared is 2y dy, correct? So 1/2 du is equal to y dy, okay? So now back to my problem. That becomes negative q over 4 pi epsilon naught times a. And then the 1/2 I'm going to take out as well. So times 1/2 to the integral of well, y dy, that's 1/2 du, so that's du right there. I have the 1/2 right here. And then that would be 1 over u to the 3/2. There you go. Okay? So now that'd be negative q over 4 pi epsilon naught times a. This 1/2 is here, and then integral of u to the, I'll just change it to u to the negative 3 over 2 du. And so when I integrate that, I'm going to get, that's equal to minus q over 4 pi epsilon naught times a times 1/2. And the integral of u to the minus 3 over 2 power is u times minus 3 over 2 plus 1, which is minus 1/2. And then the denominator will also have minus 1/2. All right, that's a rule of integration. And then 0 to a. If you didn't know how I got that, that's because the integral of x to the n dx is equal to x n plus 1 to the power of n plus 1 divided by n plus 1. Okay? So that's how I went from this to here. Okay, so we're almost there, guys. I'm going to bring out this constant right here in the denominator. So that would be minus q over 4 pi epsilon naught times a times 1/2 times negative 2. And then u to the minus 1/2, 0 to a. Yeah? So this, I can cancel out a few things, right? This 2 and this 2. And then remember I have two negative signs here, so that turns into a positive. So that becomes q over q over 4 pi epsilon naught a. And then here I'm going to substitute, what was my u again? My u was x squared plus y squared, right? That's up here, x squared plus y squared. So 1 over the square root of x squared plus y squared. Because that is the same as 1 over, or x squared plus y squared to the power of minus 1/2. Okay? And then from 0 to a. So now that becomes q over 4 pi epsilon naught a. This is not 9, that is an a. okay? And that becomes 1 over x squared plus a squared. That's an a. Minus 1 over square root of x squared plus 0, or just 1 over square root of x squared. Okay? And I can simplify that more because that becomes q over 4 pi epsilon naught times a times 1 over square root of x squared plus a squared minus 1 over x. Okay? And that is, let me move this a little bit here, but that is our final answer for the y component of the electric field produced by charge distribution Q. Okay? Oops. So now we have the x component and the y component for electric field produced by charge distribution Q. And that was what we needed to answer in part A, right? So now let's go to part B, and we need the x and y component of electric force, electrostatic force. Calculate x and y component of force that the charge distribution Q exerts on Q. Yeah, I really dislike the fact that there's a capital Q and a little q, and we're saying charge distribution Q exerts on Q. It's a little confusing, I understand, but okay. Anyways, so we need to find the x and y component of electrostatic force. So Fex and Fey. Okay? Well, the good news is the electric force, right? This maybe you should know or have in your cheat sheet, but the electric force, so F on Q, or let's just call that electric force, Fe, is equal to the electric field multiplied by the charge, right? And this charge is whatever the charge is from the point that we are at, or in this case, this guy. And remember, it has a negative Q charge. So that's going to be easy because we've already calculated in part A this guy, the electric field. So now all we need to do is calculate or multiply it by this negative point charge that was given in our problem, right? The problem stated that the point charge is negative Q. All right, so Fex is going to be Q times Ex, or the x component. Q, the charge, times the x component of electric field. The y component of electric force is going to be Q, or the charge, times the y component of electric field. So, therefore, for the x component of electric field, that's going to be equal to minus Q, that's the charge that was given in the problem, times Ex, which we solved for earlier, right? That's this guy. And I'm just going to literally just plug that in. Okay, or that's going to be equal to minus Q. Source charge is capital Q over 4 pi epsilon naught x times square root of x squared plus a squared. Okay? And for the y component of electric force, that's equal to the given charge, which was negative Q, times the y component of electric field, which we solved for right here. And I'm literally just going to plug that in. So that's equal to negative Q times capital Q divided by, or actually, instead of using a negative, instead of having this negative q here, I'm going to distribute this negative inside this parenthesis. So then I would just have positive q times capital Q, the source charge, over 4 pi epsilon naught a. And because I distributed that negative here, because I distributed that negative here to this guy, then this will be 1 over x minus 1 over square root of x squared plus a squared. Okay, and that's going to be the x component of electric force and the y component of electric force. And that is our final answer for part B.